I'm going to style of teaching from now on. I've recorded some of the long lectures out there and placed them on my courses, so I don't have to spend that much time on some of the basic concepts and some of the trivial things. Okay. So what I'm going to do in the classroom is I would be solving some problems. I would be explaining the difficult concepts. You all to be going through the video lectures. Want to learn more about anything that is interesting. There, in the videos, I discuss things more. Classroom, we cannot do that. We don't 40 minutes we have, and my time, right? So, the other handout that I gave you describes about the redox thing in organic chemistry. What is oxidation and what is uh, reduction? What's oxidation in general? In inorganic chemistry, we have metals, for example, KMnO4. We can find out the oxidation of potassium, we can find out the oxidation of manganese, and we can find out the oxidation of oxygen. But how do we know that? Because you see the oxidation states. Is it plus 7 or plus 6 or plus 5 or plus 4 or minus 1, minus 2? So we have oxidation states in inorganic. But we have an organic oxidation. We don't have that kind of process in organic chemistry, right? Because we say that organic compounds are made up of carbon. Carbon is a non-metal. It's a organic compound. But no point is giving up its electrons. If it doesn't give up its electrons, we cannot say that it has a good oxidation. But oxidation is loss of electrons. That's why we have oxidation process. If any metal loses its electrons, we say that that metal has been oxidized. But in carbon, there is no electron transfer, complete electron transfer. What we have is covalent bonding. Coordination covalent bonding at the maximum, right? That means each of the partners that are bond forming, participating in the bond formation contribute one electron each, and as a result, carbon makes 4 bonds. Let's say we take the example of methane. This is not how the structure is. That structure is tetrahedral in nature, but carbon is contributing 4 electrons in 4 bonds. The hydrogen is contributing 1 electron each. So they're kind of satisfying their octet groups. The valency has been fulfilled, and we say that this is a stable compound. But what is the oxidation number of carbon in this compound? Do we say it's oxidized or do we say it's reduced? There's no defining oxidation in copper, right? So we have come up with organic chemistry to have a different way of defining oxidation and reduction. Anything, any kind of carbon is forming a bond. If it is forming a bond to more electronegative atom, let's say oxygen, okay, and we'll compare that to this. So which one is more oxidized? There is something else attached to oxygen. I haven't attached that. Let's see. It's not good. R is a wild card in all that. Could be anything. If carbon is attached to more electronegative atoms, carbon is attached to oxidation level. Let's another slide. We have an alcohol. We don't know what the three groups are. Let's say we have an alkane. And sorry about that. Let's just have something like this. Let's say we have resistance that may not have resistance. I just wanted to draw them out. So this is the most, the least oxidized carbon, or the most reduced carbon of the series. This is the most oxidized carbon compared to this, because it has 4 bonds to oxygen, whereas this has 3 bonds. This has only 2 bonds to oxygen, and this has only 1 bond to oxygen. It has none. Right? Carbons are hydrogen, but not anything more electronegative than carbon. At the maximum, it is attached to a carbon itself. Right? So, we say that this is the oxidation of alcohol level. So we have oxidation level. And we say that this is the oxidation of aldehyde level because aldehyde is what? That's aldehyde, right? It has 2 bonds to oxygen. It's got 2 different bonds, one is sigma bond and one is pi bond, but it has 2 bonds to oxygen. The balances of this bond are satisfied through the bonds to more electronegative atoms. It has 2 valencies satisfied by oxygen, so this state is called the oxidation level of ketone or aldehyde. So anything that has 2 bonds to a more electronegative atom is said to be at the oxidation level of aldehyde. So for example, this is called dichloromethane, which is going to be hydrogen, or if it is the carbon, also it's called dichlorocarbon, right? In the sense that it is making 2 bonds to more electronegative atoms than itself. So chlorine solution is true with the chloroform. Chloroform has 3 bonds to chlorines, and this is said to be at the oxidation level of esters. What is the oxidation level of esters? Esters have 3 bonds to carbon, so that's the oxidation level of esters. So we refer back to this functional rule to describe the oxidation. Anything that has 3 bonds to heteroatoms, more electronegative than the carbon itself, then ester. What is the most oxidized state of carbon? 4 bonds, right? Carbon dioxide is the most oxidized form of carbon. For example, start off with methane. Let's say fill some alkane in your and combust it. Lost the connection. Okay. So we fill the gas, that is petroleum gas, in the car, and we use the catalytic converter and we oxidize it in the engine, and we get carbon dioxide and we release some energy, and that energy is used for running the motors, the car. So this process is called combustion, and we have more reduced form of carbon oxidizing to carbon dioxide. The carbon dioxide cannot be further oxidized. Okay. So what is the oxidation level of this carbon? This is said to be uh, at highest oxidation level. So if you have 4 bonds to carbon, for example, this also is called a compound. This is called carbonate. And carbonate is also at oxidation level of carbon dioxide. So the oxidation is defined as addition of more electronegative atoms or addition of oxygen itself. Addition of electronegative atoms. What is the reference? Carbon. Carbon is itself a reference point. You are looking at the electronegativity of the atom and deciding whether it is more electronegative, you say the carbon is oxidized. Less electronegative, you say the carbon is oxidized. For example, if you are adding hydrogen, that process is called what? Addition of hydrogen to carbon is defined as reduction. Right? And the opposite is true too. Addition of oxygen is oxidation. Removal of hydrogen is also so, addition of oxygen is oxidation or removal of hydrogen is. So let's take some examples and sample. Don't worry, all this is given in the handout. Okay? Just try to get the concept down, take a note. Because it's from the handout, there's no concept. So, let's say we have double bond compound. We add hydrogen to that. What do we get? What are we doing here? Are we doing oxidation or reduction? Reduction. And let's say we are doing a dihydroxylation. So what do we call this process? Oxidation, right? This is reduction, this is oxidation. Let's say I had a way of converting this back to, I can do this process in the lab. I just have to use palladium. Here I use palladium and hydrogen. When you use palladium and hydrogen, you are adding hydrogen across the double bond. That's called reduction. If I just use the palladium source, I don't use hydrogen. Palladium has affinity for hydrogen, so it removes the hydrogen. What do we call this process? Wash. Oxidation. You are removing hydrogen. So you are not quite adding oxygen. So the removal of hydrogen is termed as oxidation. Addition of oxygen is termed as oxidation. Addition of electronegative acid is termed as. So you have to be informed with these concepts, these reductions and oxidations. We visit you time and again. So I thought of spending a few minutes on that. And the handout, one of the handout explains this whole thing. That is very fundamental to organic chemistry. Any questions about oxidations and reductions in organic chemistry? So if you take the functional groups, we had alkanes, we had alkenes, and we had alkynes. The bond angle is not quite right here. When you draw alkynes, you make sure that the bond angles are 180. Okay? At least these four carbons should be 180 angles to each other. This is wrong drawing. Sometimes this bond angle is representing that bend, but it's not bend. It's in a structure, right? Because it's an ST carbon. ST carbon can only make bond at angles 180 degrees. So that's actually drawn as a linear molecule. Okay. And we have alcohols, we have alkyl halides, and we have aldehydes, we have carbonyls, we have carboxylic acid, amides, these two R groups on nitrogen. I'm on the computer, so I cannot draw them properly. Amides. Can you think of any other functional group that you learned? This is amide. Okay? Acid chloride, esters. So what's happening as we go from alkanes to other functional groups? Carbons are getting oxidized. Alkenes at a higher oxidation. But the heat more oxidized carbon, more oxidized. But anyhow, reduction of the hydrogen content in the molecule. These are all said to be at the same oxidation level. Oxygen is more electronegative than carbon. Other groups go higher oxidation level to come across aldehydes and ketones. Further oxidization is oxalic compounds, and all these are the same. Because the carbon is attached to three heteroatoms. This carbon is making two bonds with oxygen, one bond with the nitrogen. This carbon is making two bonds to oxygen, one carbon to chlorine. So in total, the oxidation level. But if I have to go from this to an alcohol, I have to do an oxygen. Okay? Or if I have alcohol, I can go back to alkane by using that. So this is network. Whatever you learn in network, you will come back. So we are talking about alcohol. We will looking at the ways of making alcohol, then you have to remember hydration of alcohol. This is a not alcohol, non-alcohol. You can make alcohol. So there we study very reactive property of heat, but here you are studying that you cannot forget what you learned. This is one, got to remember all those reactions. And this is the hierarchy of the oxidized functional. What I mean by that, we'll take one example of alcohol. So we have different types of alcohol, nature of the carbon. This is the C3 hybrid carbon, but this is the primary carbon. This is the secondary carbon. That's the tertiary carbon. What am I looking at? I'm looking at the carbon content on this carbon. I'm not worried about other groups. This has a tertiary butyl group. This is not a tertiary butyl at all. Because the hydroxy group is attached to primary carbon. The primary carbon is the one which has two bonds to hydrogen. Right? At least two bonds. And this is the secondary alcohol, but because that's the secondary carbon, this is the tertiary alcohol, that's the tertiary carbon. Then we have quaternary alcohol. We cannot have quaternary alcohol because quaternary carbon the valence is that. So let's take one compound now, which has another functional group like that. So it has carboxylic acid, also has alcohol. So we will call it as carboxylic acid or we will call it carboxylic acid. I just had one alcohol that I drew before. I will start numbering at this carbon, go this way, and find out the longest side chain. And then side chain, so I put bute for that. What's happening here? Sorry about it. So that's the bute. Let's derive from the parent carbon side chain, 4 carbons. This is not high. Numbering of that carbon. Okay. So I have 4 carbons in my parent chain, and then I have 2 substituents at carbon number 3. So those 2 are metals. So I would say 3,3 dimethyl bute. Because there is no unsaturation. If there is unsaturation, I will go with E or P, alkyne. Okay. See how the name is derived. This is the substituent description. This is the parent hydrocarbon description. This is the functionality in the side chain and the parent chain. Sorry. And now we have to come to the actual functional group. It's an alcohol, so it's called OL. Okay. So this is now suffix. Alcohol is the parent compound, so OL is given this description of the hydroxy. So the whole name of this compound is 3,3-dimethyl butanol, and that is the head of the house, right? This is now regarded as the primary functional group, and your numbering starts from this end. And in this case, your numbering starts from here, and then you name this as a carboxylic acid. Have a different functional group, which is at a higher oxidation level than oxy group, which is hydroxy group. Prefix instead of suffix. Huh? So let's number this 1, 2, 3, 4. This is also, but here this is oleic acid, so the suffix for the carboxylic acid, and butanoic acid because oleic acid is for the functional group. And what happens to 4 hydroxy, 3 dimethyl, is a 2 dimethyl, butanoic acid. So got to recognize that some functional groups are parent group functional groups when there is nothing else. There is something more higher operation level that we can that, that is for that is the suffix for carbon. You learn that more in carbon. to do is you use general way of nomenclature. Don't have discussing these functional groups. Once you know IUPAC, you can apply to so this one 4-hydroxy 2,2-dimethyl ammonia. Then the parent carbon. The two methyl so, oxidation and reduction has significance in organic chemistry. The more oxidized the functional group, the higher the priority it gets. So, all these things, and there is a primer in one of the resources that I placed online that describes the IUPAC nomenclature of all the functional groups in one shot. Okay, so let's now go to the alcohols. We already looked at the three types of alcohols: alcohol, secondary alcohol, tertiary alcohol. That's one classification. There is another classification depending upon what is attached to, and all these compounds, if you recognize, they have hydroxy groups. So there is general hydroxy compound, alcohol, alcohol. There are different types of alcohol. This is an sp3 carbon. If I'm not drawing hydrogen, right? Who is not getting tight and then stepping on that. Okay, so that's an sp3 carbon containing hydroxy group, so it's called simple alcohol. And this is sp2 hybridized carbon, so that's called enol, because this is the carbon where the ene is starting from, so it's called enol. Enol. You already learned that in keto-enol tautomerization. But if I had an alcohol like this, that's not called enol, because the hydroxy group is not attached to the sp2 carbon. Though there is sp2 carbon in my compound, but it's not directly attached to my hydroxy group, so I cannot call this as an enol. Got it? Enols are those which have hydroxy group. This is simple alcohol. And if hydroxy group is attached to phenyl group or any other aromatic group for that matter, it doesn't have to be phenyl. This is called phenyl when it is a substitute. The benzene ring, but when benzene ring becomes a substitute on something, something is attached to phenyl, benzene ring, then this is formed as phenyl group. So that alcohol is called as. Okay. It could be another aromatic compound. For example, the hydroxy group could have been attached to a thiophenol. Sulfur is the pi number containing compound, and the hydroxy. So this is also planet called. Okay. So phenols are those where the hydroxy groups are attached to sp2 carbon, but that sp2 carbon is in the sextet of aromaticity. If I just had this compound, for example, how do I name that? What do I call it? Just a general term. So you got to say cyclopentanol, but for now it's enough to recognize that as enol, right? If I had an aromatic ring, then it would be a different case. For example, if I had an oxygen and that's a double bond there, and that's a furan molecule, furan is aromatic. Right? So the properties of these alcohols are different than the properties of these alcohols. Nevertheless, all of them have one functional group, that is hydroxy group. So some of the reactions will be generalized as R. But let's look into the structure and bonding. I've already made a video on the details of that. I've placed the link on my courses. Alcohol, oxygen, So these can be regarded as derivatives of water. That's water structure, right? You learn in 10.52 or what is the hybridization of oxygen here? What is the hybridization of oxygen? Right? sp3, though it has only two bonds to hydrogen, it would be misleading to you to think that this is sp hybridized, but if you draw the structures out, there are two p orbitals which are kind of hosting two not p orbitals. This is sp3 orbital, which is hosting pair of electrons. This is a hosting pair of electrons, and we have two hydrogens attached to oxygen, and the bond angle is, if it is sp3, what is the bond angle should be? 107? 107.35. Okay? But the bond angle in alcohol is really deviated from that. Right? Here we have two lone pairs, they repel each other, so the bond angle goes to 110 of water, not sure what exactly the number is. But here the bond angles go to the lower side, which is around 109, because now we have another bunch of electrons. You know, atoms and molecules are more. When you are trying to force bigger groups, the bond angles change. For example, if I have an ether, then I have two R groups attached to oxygen. The bond angles of this would be much more compressed. It would be like 120 degrees. Sorry. So 180 degrees. Why? Because these two R groups are two clouds of electrons. They are trying to get carbon. As a result, they have to be more accommodated. So the lone pairs would now squeeze a little bit and then the bond angle would change. So anyhow, the take home point here is that oxygen is quickly hybridized. One side you have R group, the other side hydrogen. So this can be defined as a derivative of water. Alkylation product of water is alcohol. That's why we call it as hydroxy compounds. So whatever the properties of water that you learn are quite transferable. What are those properties that you can recall? Oxygen is more electronegative and I have as an example. So one polarization here. Oxygen is more electronegative, so the electron density is pulled towards oxygen. As a result, that's the dipole arrow, that's the delta negative charge, and that's the delta positive charge. So oxygens are more electronegative, they polarize the bonds, and the negative dipole and this positive electron. This hydrogen is not completely happy. Of this orbit, right? So this hydrogen, instead of being loyal to one oxygen, this would be shared between two oxygens of different molecules. So what it does is it forms a hydrogen bonding with another molecule. Let's say another methanol species comes out of cross and then you have delta bonding. What is this bonding called? It's weaker than covalent bonding, but stronger than van der Waals forces and all those forces. That's the reason why it's called hydrogen bonding. The hydrogen bonding doesn't stop here. This hydrogen can now participate with some other molecule, and as a result, we have extensive of hydrogen bonding. It's so extensive that all the molecules are hydrogen. That's the reason why we have hydrogen bonding. That's the reason why we have water. Yeah. Hydrogen bonding associated with one another and it affects the system. It's so important that many of enzymes that we have hydrogen bonding is very critical for existence of life. There is a weaker bond, it has very profound effect on the properties. So what we conclude here? Structure has control over the property. know, if you know the structure of your compound, you can predict the property. You can predict physical as well as chemical property. How is hydrogen bonding controlling physical property? For example, why is bonding different? If they are solid, they are higher melting points. Okay, and they have more water solubility. Alcohols are soluble in water. Ethanol and water. Ethanol can not only form water, but when you have associations, methanol we had alcohol like about just drawing that then hold me on the structure. You have about 20 carbon side chains, then the miscibility would go down. It would not be miscible in water. Water on it would precipitate outside the water because it cannot form the hydrogen bond. So the alkyl side chain has some role, but the properties of alcohol are controlled by the hydroxy group. Okay? Especially the chemical properties. Physical properties are controlled to some extent by the R group as well, but nevertheless, the chemistry of this whole molecule is dictated by the hydroxy group. There's not much chemistry for the alkyl side chain, right? That's the reason why we call this as a functional group, because that's where so we focus on functional groups of different types in Chem 252. We start with alcohol. We also focus on ethyl. Just to give you some examples. And we focus on aldehydes. We would discuss something about carboxylic acid, talk about esters, talk about amide. Okay? So they're all interconverted. So whatever you learn in alcohol chapter will come back in other chapters. Whatever you're going to learn in other chapters will come back in chapter. So the interdependence we will be dealing all okay. So your book is divided into different chapters. We would be having general discussions. For individual lectures, I'll be giving on the handouts as well as the lectures. Okay? So alcohol, right? We talk about alcohol. Let's look at the alcohol functional group, and we already know physical properties. But what about the chemical properties? This is called a protic compound, right? Why? For example, water. No water in and out, you should be good in alcohol. Water can act as a base and can donate the proton. Base reaction for water. Let's say we bring in a base. In that case, water would act as what? What would water do? It would give out the proton. As a result, this only has one bond now, and it becomes hydroxide. Whatever is gaining the proton, it becomes positively charged. And this is called equilibrium. All the acid-base reactions are equilibrium. You have very strong acid and very weak base. Okay, so whenever you write the acid-base reaction, you have to use the equilibrium arrow. That's equilibrium arrow. And base is picking the proton here. So the arrow starts from base and goes to the proton. So it's subtracting the proton. So it's donating the pair of electrons. That's why this is called base. Okay? And this is donating a proton. That's why this is called as an acid. Or this group is accepting a pair of electrons from base. That's called acid. So you have Lewis acid definition, Bronford acid definition. Bronford definition, donor of a proton is an acid, acceptor of a proton is a base. What do we have on this side? We have conjugate acid. So the acidity of this group given by dictated by stability of the conjugate base. If I look at my conjugate base, if it is stable enough to survive on its own, how do alcohols compare to that? Water equilibrium is balanced, right? Just like balance at pH 7. You have at pH 7, water is existing as hydronium ion and a hydroxide ion, equilibrium between hydronium ion and a hydroxide ion. Or to write in a different way, let's say we have a reaction between two water molecules. One of the water molecules is acting as a base, the other one is acting as an acid. So we have hydroxide plus H3O plus. What's happening? This is taking the hydrogen of that proton. So these electrons are pushed to the oxygen. So this is becoming OH minus. This is gaining the proton. This is called hydronium ion. And this is an acid-base reaction. So we need to use the equilibrium arrow. And if it is forward direction, if the equilibrium is lying towards forward, use the bigger arrow to show the forward direction. If it is going more towards backwards, so use a bigger arrow to show that direction. But in this reaction, I use an equal size of an arrow. This is an equilibrium arrow because this side is as much favored as this side. So the water at pH 7 can exist as hydroxy group and hydronium ion. Itself is acting as a base. These alcohols act as amphoteric. They act as a base, or they can act as acid salvage. Talk about acid, you will use the reaction on the hydrogen. When you talk about base, you use reactions on somewhere else, right? So let's talk about the acid properties. So if you have an alcohol, now onwards I have just used an R group, and I will bring in a base, and it's an equilibrium reaction. So this base is taking proton, and this electron pair is pushed to oxygen. So you have plus EH. B is gaining a positive charge because it's donating electrons to hydrogen. Okay? So this is your conjugate base. And if it is stabilized, this direction would be pushed towards this side. If this is not stable, what would it do? It would pick its own proton and go back to this side. So weaker side of equilibrium is favored. The equilibrium lies towards, we have 5 more minutes because this watch is 5 minutes faster. I'm going to ask them to fix that. Okay? So the equilibrium lies to the weaker side, that means whatever this is strong base, conjugate base, pick the proton and go back. This is strong acid. What do we mean by the stability of the conjugate base? Depending upon the nature of R group, if R is electron withdrawing, let's say we have CF3OH and we have CH3OH. Which one is the most strong acid? Sorry. Okay. We have CH3O minus. We have CF3O minus. That's whatever the base. I'm just going to use B for base. Okay, so we have two alcohols, trifluoromethanol and methanol itself. The methoxide is not as stable as helping this oxygen to get rid of some of the burden it is carrying. What is the burden? If we have already electrons, lower the electron density, so it's stabilizing this oxide. So the equilibrium lies towards forward side. Trifluoromethanol is a stronger acid compared to methanol because that oxide, methyl group is donating the electron. So all the acid-base properties can be explained by looking at the stability of the formula. How does that compare? And we have a cyclohexyl. Upon donation of a proton, phenol would become phenoxide, cyclohexane would become cyclohexane oxide. But this phenoxide has resonance. In other words, this electron density can be drawn into the panel ring. Panel group is acting as electron withdrawing group, but we cannot provide more resonance for this. Cyclohexyl alcohol is not as acidic as phenol. Phenols are more acidic than alcohol. Those both made up of 6 carbons, though they have 2 hydroxy groups, which are similar, but the acidity of this is much higher than the acidity of this. We'll continue in the next class. So to let you know once again, the exam is postponed to the next Monday, not this Monday. Not until 18th, it will be postponed to 24th. Yeah. Homework because the chapter 17 would pile on you, so I want you to finish chapter 13. To post this very lecture online again. If somebody wants to view, you can view it.